It's a very sophisticated and nuanced field. And, to start with a question like, if somebody says like there weren't dinosaurs, that's kind of like telling a planetary scientist like there's no Jupiter.
It feels a
It's
little
just,
flat Earth to me. Like
well,
when people say that, because there's just when I see things that have such significant evidence, and it's like where do we get all this stuff from? It just came out of thin air.
yeah. So I can tell you one thing, which is one way to demonstrate it is, so now there's a field called molecular paleontology.
Molecular paleontology.
Yeah, and so we can, and we do this in my lab, we can demineralize dinosaur bones and recover routinely now. They're proteins in blood vessels and bone building cells. Proteins have hereditary information in them. It's not as robust as DNA, but you can sequence proteins and make family trees from them. And this was started by a friend and colleague of mine, Mary Schweitzer, she used to be at North Carolina State. And we've exchanged lots of grad students and done some of this work. You can sequence these proteins, and then if it was contamination or something, it could fall out anywhere in this giant database of proteins. But if it's really from a dinosaur, it's going to fall out next to their closest living relatives, which are crocodiles. Crocodiles aren't dinosaurs, but they're the closest living relatives.
They look like it.
And birds. Birds are literal dinosaurs.
Literal.
And we sequence these proteins, and they fall out between birds and crocodiles. And so we have molecular evidence that these things are what we think they are, that they are dinosaurs. And of course, we have the skeletal evidence as well. And we can see it in, the geological record is like a layer cake, right? Except you don't get the whole cake anywhere, right? You get this piece of the cake here and this piece of the cake there. But we know when dinosaurs first appeared. We know how long they persisted. We know exactly when they end. And it doesn't matter if you're in Afghanistan or Antarctica or New Jersey or China. They always start and end exactly where we know them to start and end, right? Like they behave geologically. They're predictable. It's obvious that that's the story.
Yeah. Now, approximately how many years ago did the first dinosaur that we know of walk the Earth?
The first dinosaur was about 237 million years ago.
Okay.
So that's the Triassic period.
Triassic period.
Yeah. The Mesozoic, which is the time of dinosaurs, is Triassic, the now famous Jurassic, and the Cretaceous.
Okay. Now, how do we, again, a million questions. How do we mark off those eras? What behaviorally or that we can observe from dinosaurs makes it change officially from one era to the other?
They're all defined by extinctions. And there's a commission called the International Commission on Stratigraphic Nomenclature.
What a name.
Yeah.
Yeah, I'm going to get them some rebranding.
And yes, they could use it. And it's a large group of scientists, and they define these. There's eons, and there's eras, and there's periods, and there are epochs, and they all fit inside each other, and they define what the boundaries are based on the extinction of certain organisms or the extinction of groups of organisms. And the big boundaries have to do with big extinctions. So the end of the Paleozoic, the start of the Mesozoic, which is the time of the dinosaurs. That happens when we have the world's worst mass extinction. It happens about 250 million years ago. It's 255. It's the end of the Permian period. We lose 95% of species on the planet. So if you're a geologist or a paleontologist and you're working in rocks that are around that boundary, it's very easy to tell which side of the boundary you're on because 95% of the species disappear above that. When the dinosaurs go extinct 66 million years ago, that's the end of the Mesozoic era and the start of the Cenozoic era, which we're still in. Again, it's very easy to tell you're at that boundary because 75% of the species go extinct there.
But the 75%, that was going to be my next question, the 75% that goes extinct includes all dinosaurs, except for birds.
That's right.
Okay.
Yep.
Fascinating. So when dinosaurs were first on the Earth, because like most of us out here are looking at this from a layman's perspective, and we think about, oh, Jurassic Park, T-Rex running around, raptors, all that. But when they're first on the Earth, what were some of the, recognizable dinosaurs that we might know today that existed in that, I forget the name of it, the Triassic period?
We're actually sitting on the Triassic here in Hoboken.
We're sitting on the Triassic?
Yeah.
What does that mean?
Well, the Triassic is the time when the supercontinent of Pangea breaks up.
Right. That's what I was
And
looking for earlier.
that means the Atlantic Ocean basically starts to unzip, right? And there was a time when you could stand here in Hoboken and look about a mile across the ocean to Africa.
That's so cool.
And so, the Palisades, which go right
Yeah,
up the river here, those are basalt flows. Basalt comes from magmatic eruptions of ocean-type magma. And that happens here when the Atlantic Ocean forms, when Pangea rifts open. And all the gas that was released during that rifting caused the world's fourth mass extinction. So the evidence of the fourth mass extinction is in the Palisades along the Hudson at the top of New Jersey, and the evidence for the fifth mass extinction is at the Fossil Park in southern New Jersey.
Not to be confused with my Vinnies and Carmines out there who are looking at other types of extinctions that have happened in the Palisades.
That's right.
Just got to throw that out there. There's
Yes.
been a few since then.
Yeah.
But wow. So it's crazy because you just wouldn't think that. I mean, look at the wall right here. What's right across the river? This is what we have here now, and the idea that there were like dinosaurs running around here, or where it was underwater and the land's over there and the dinosaurs are right there. It's just crazy.
At that time, 255 million years ago, this was an apocalyptic hellscape. This volcanic fissure. It was just.
It still is. All right. So the Triassic period, though, the very first one. So, what types of species? Let's start with dinosaurs.
Dinosaurs
what types
are
of species
small.
exist?
Dinosaurs are about the size of a house cat.
Oh, wow.
Right?
So they could be a pet.
They could menace nothing bigger than a bug at the time.
Wow.
They evolve into probably the hardest time on Earth since there's been complex life on Earth, because we've just had this horrible mass extinction at the end of the Permian period. Almost everything is dead. The complex life on planet Earth almost goes out of business. And the first thing that kind of gets the jump, back are crocodiles. And so we're kind of living in a crocodile world. In the Triassic period. There's an 8-foot tall bipedal crocodile in the Triassic period.
So it's running after you.
It's like Wally Gator from hell.
Yeah. No, thanks. I'm out on that.
And so dinosaurs evolve into this world, and they don't really make a lot of headway because of the crocodiles dominating everything. So they're small, they're kind of spindly. The oldest one we know of at the moment is Nyasasaurus from Tanzania.
Can we pull that up? Nyasasaurus?
Yeah.
Let's do that.
But it's tiny. And they stay that way until the fourth mass extinction, which we have the evidence for right along the Hudson here. And for some reason, that kind of knocks back the crocodiles, and the dinosaurs. The dinosaurs are the ones that get well, no, that's kind of a crazy. I think that might be a CRISPR accident right there.
That's like
a watermelon and a lizard or something.
That's why I was looking at Ben. I'm like, don't you open Pandora's box too badly here, my friend. He's like going to come out with like, oh, it's a velociraptor. Sorry.
Yeah,
it's twice the size now.
It's NYSSA.
NYSSA, we got it, Joe? What are we looking at? Yeah, we got to make sure we get it right so people aren't seeing a new demon from hell.
NYASS. Yeah.
Okay.
Right. But it's a little spindly dinosaur.
And you said it was like approximately this size?
Yeah, there we go.
Which one do you want?
I think that the picture on the upper right looks
right
good.
there. So this thing would have been about this big, you're saying?
Yeah, I mean roughly the size of a cat. Right. And so, they're not too tough.
Now his legs are on the ground bipedal, and then he's got hands, but he's still hunched over in like the position of a cat at the time.
Yeah. Early dinosaurs were all bipedal, these kinds. And the thing that is different, the thing that makes dinosaurs and separates them from their reptilian kin. Think about a lizard. They have a very sprawling, languid posture with elbows and knees bent. Belly on the ground, tail dragging behind. A lizard is always like a half a push-up away from taking a nap, right? That's not dinosaurs. Dinosaurs have their legs under their body.
Yes.
Their ankles are hinged for straight ahead forward motion. They have very strong hips. They have at least 3 sacral vertebrae that connect one side of their hip to the other. So it makes like a strong bone box to which you can attach powerful leg muscles. So dinosaurs are more like mammals in that we're fully upright creatures that, stand mostly, not lay mostly, and are ready to go. So they're vigorous creatures.
Why evolutionarily do so many of them have like almost no arms? Like we make the joke about like T-Rex arms, but it's a scary T-Rex and its arms are like in here as opposed to like a humans that are out here.
Well, some do, some don't. I mean, if you look at in that same group of dinosaurs that T-Rex is in called the theropods, look at something like a Therizinosaurus.
Therizinosaurus.
Yeah. Now, a Therizinosaur
Sounds like a drug.
They could be like 17 feet tall, fully feathered, not a bird, but a fully feathered non-avian dinosaur. Yeah, look at like that middle picture. Big pot belly, and then they have like these meter-long Edward Scissorhands claws. So it's a nightmare, basically.
Whoa.
And so you can see some dinosaurs that were bipedal had very long arms. Others had very short arms. Now, in the case of T-Rex, people make fun of its little arms, like if you're happy and I'll never mind, or, T-Rex can't answer the phone and all this stuff.
Yeah.
Well, those tiny arms of T-Rex make its murderous bite possible. Because if you're going to have the strongest bite that any land animal has ever had, you need really big jaw muscles. And if you're going to have big jaw muscles, you need a big head to strap those jaw muscles onto, right? So you need a big skull. If you're going to have a really big skull, you need really big neck muscles to hold up your really big skull. And neck muscles and arm muscles compete for muscle attachment space on the shoulder girdle.
Whoa.
So you can't have both. So as its head got bigger, as its bite got stronger, its arms got littler to allow for that muscle attachment space. So the next time you make fun of its little tiny arms with the 2 little witchy fingers on it, think again, because that's what made its killer bite possible.
It automatically has it, whereas I got a deadlift to get this right here, pretty much.
Pretty much.
Wow.
Yeah.
Now, how did they go? I mean, obviously that story makes total sense, and we see where it ends up because we know a lot now, but evolutionarily, when they were first discovering like the T-Rex or something, which I don't even know when that is, maybe you can enlighten me.
1905.
1905
for T-Rex.
1905. Okay. What did they do to determine that story that you just explained scientifically? Is it just like deductive reasoning, or do they find other pieces of evidence that show like, their shoulder muscle developed this way, or their traps develop, whatever they're called, develop this way over these 300 million years? How does it work?
Well, that particular story that I told is the work of my friend, Dr. Michael Habib in Los Angeles, who's a biomechanics genius, I would say. And so that's his hypothesis. But, when we look at dinosaurs, we mostly have their bones, although in some cases we have other parts that survive and we recover. And bones have muscle attachment scars on them. And from those muscle attachment scars, we can estimate the size and the power of certain muscles. And so it helps us reconstruct these creatures. It helps us reconstruct how they move. And it's also the bones are the primary defining features for us. And so, if we're in today's world, and we want to know, like, is this a species or is this a species? Well, we look to see who can produce viable offspring with each other. In the ancient world, we don't know that, right? We just don't have that evidence. And so the definition of a fossil species is that it has to be, you have to have a morphological definition of that species made by a competent paleontologist that can later be recognized by another competent paleontologist. And to define a new species, you have to find a feature in the skeleton or the fossil that hasn't been seen in any other animal that's closely related. We call these autapomorphies, but it's just a fancy name for a novel feature in the skeleton. You need at least one. It's maybe not great practice to define a new species based on just one. But when you assemble a group of them, then you have a clearly defined species that another paleontologist, maybe 100 years from now, could recognize if they find the same species.
It's like a constant building upon of peer review in a way over time.
Yeah.
Got it.
Yeah, and like in any science, paleontologists can be a quarrelsome lot. That's what we're supposed to do in science, is we challenge each other, right?
That is correct. That's how it's supposed to be.
Yeah,
Yes.
Because in science, what we say is, if you listen closely, you will almost never hear a scientist say that they have proved something. We don't really use that term very much. What we say is that we have failed to falsify something.
Failed to falsify.
Yeah, and
like
so
that.
you create a hypothesis, and then you try to poke holes first in your own hypothesis, and then you publish it, and you let all the other scientists try to poke holes in your hypothesis. And if it withstands all that, then we say we have failed to falsify that hypothesis, which means we have gained confidence
Yes.
in that hypothesis. Sometimes hypotheses become, they're tested so frequently, and we have so much confidence in them that historically some become laws, like the law of gravity, which is really just a hypothesis.
Yeah.
It's a prediction, but it's a prediction that's so good that people are willing to strap themselves to rockets and shoot themselves into space based on that hypothesis.
Yes.
Right? And so that's essentially how science works. So nobody says, we've proven the law of gravity. You would say that we have immense confidence in Newton's gravitational formula because no one has ever falsified it.
I've had the privilege of having some pretty amazing scientists in here over the past, especially couple years. Started with Michio Kaku and eventually had in Brian Keating. And recently I had in Claudia de Rham, who wrote what was a controversial paper on gravity. She was working on this for years and years, but I think like when it really blew up was like 2018. And she, for one, was even saying like, oh, the gravity we know isn't everything. Right. I found this, I'm going to state it all wrong, so go listen to episode 311. But, she's like, or 310. I found that gravity is according to what Newton has, but there's a molecule or something that is also missing, and here's why it makes sense mathematically. And I bring this up because to me, the beauty and also madness of science is that literally the most brilliant people in the world are usually the people who are in that space. It's amazing what they're able to do. You can look through history, look at the Einsteins, look at the Newtons, go all the way back to Galileo and just see the pieces that they were able to put together that we could later build on. But the madness of it is that in a way, they're always figuring out the latest thing that can't be falsified so that someone else can build on top of that and eventually at least falsify a lot of it, if not all of it, to get to the next step that then follows that process to get all the way to eventually the top, which is trying to figure out the meaning of life and everything. And yet we will be able to look back on scientists who maybe objectively got most or all of what they discovered wrong as the people who actually trailblazed us to get to the answer. It's like this amazing catch-22 or paradox. Do you ever think about that with what you do in
it's
paleontology?
exactly right. When you if your work is falsified, you're making progress.
Yes.
Right? There's an example. There was a guy named Bishop Ussher. He was the primate of Ireland, which I learned is a religious title, not his simian origins, but he was.
We gotta check that with YouTube monetization. Just to be clear.
He was an archbishop in Ireland, and he decides this is in the 1600s, I believe. He decides he's going to figure out how old the Earth is, and he has no tools. Right? Geology hasn't been invented.
It hadn't been invented at all.
Not really. No. That comes around. James Hutton published his theory of the Earth at the very end of the 1700s. So we don't have geology. We obviously don't have any kind of lab tools to date rocks or anything like that. So he doesn't have much to work with. He's an archbishop, so he's got the Bible, right? So he does some historical research, and he figures out the date of King Nebuchadnezzar in the Bible. And so he's got a starting date there. And then he goes back through all the begots in the Bible, and so he works his way back through the generations, back to Adam and Eve, and he determines that the earth was created in 4004 BC on October 23rd around 6 p.m. On a Saturday.
Oh, we landed on the time too.
Yeah.
Wow. Hey guys, if you haven't already subscribed, please hit that subscribe button. It's a huge, huge help. Thank you.
Now, you can laugh at that, especially because it's absurdly specific. But what Usher did was he created a testable hypothesis,
Yeah.
right? And we have tested that hypothesis and we have falsified it. But it was a credible piece of scholarship, I think, and we falsified his hypothesis, and that's what we call progress.
Did he say how he got the time? Did he ever like give a good
I
answer?
don't know how he
Or
got
did
the
he say
time
like
of the
God
day.
told me that was the time?
Not really sure.
God feels like a post-happy hour kind of guy, right?
Maybe.
That might be it.
Yeah.
You know, we weren't drinking at 5 and creating the Earth. We waited till after everyone left the bar. That makes sense. No, but it's almost like an extreme example, but it's another great example of what I'm getting at. It's
And
like,
so, I mean, scientists are people,
Yep.
right? We have our time and our careers and you know, maybe our egos invested into things, but
they have ego in science. They don't have
a few
that.
of them do. Yeah, not me personally, but some of them, you know. And so this is hard to do. But the proper response of a scientist, if your idea is falsified, you say like, great, we've made progress.
Yes.
Right?
And it's the ultimate, again, that's like another paradox with human nature, because your ego's like, but does that mean I'm full of shit? Which is not the case, but that's how things will get painted. Like, oh, you were the guy that was wrong. But that's the whole point. You're supposed to try to explore the unexplored and figure out what that is. And I think we should celebrate that.
I said on, I think, the Discovery Channel like 25 years ago, that we would never recover ancient molecules because of all these reasons why they would never survive. They would degrade over time. Well, we did.
We did. Can you explain that?
And I was wrong about that. And so, you know, I'm a scientist.
Thank you for coming clean.
Well, scientists change their view when they get new information.
That's right.
That's what makes science different than politics. That's what makes science different than religion, right? I mean, how many times have you had a political argument with somebody where like you have like this killer fact and it doesn't change a thing, right? Or how often does an event happen in the world or a new discovery in the world, and how often does that change religion? It doesn't.
It doesn't.
Right? But it does science, because that's what science is, right? And that's what makes it different.
Yeah, and I wish everyone could think that way, because we've seen, you know, especially over the past couple of decades, people from outside the space, I might add, in many cases, turn science into like the new religion and stuff like that. And the whole, again, it takes things and suddenly defines stuff as law, and then you're not questioning, you know, whether or not we can test something. And it exists across all elements of science. And I talk with all the guys I bring in here about it because it's so counterintuitive to me. It's like we should constantly be testing questions. And if something is then proven is like, oh, that's not right, then great. We've made progress, just like you said.
Yeah.
So going back to dinosaurs, though, and we were talking about the fourth extinction when that happened.
Mm-hmm.
What you might have mentioned this, but I just want to make sure we rehash it. What exactly caused the fourth extinction, where I think you said 95% of species were wiped out? Like
in the third, 95% of species. In the fourth, it was about 75, bad.
So this is like 250 million years ago, 255 million years ago?
The fourth was 200. The third was 255.
That's the one I wanted to ask about.
Yeah.
Let's start at the third. So what caused the third extinction?
Yeah, we call this the Great Dying. There's a couple things. There's a lot of things that are going wrong on the planet at this time. One is that people think, you know, a lot of people know the word Pangea, right? The supercontinent, and they think that that's how continents started. It's not how continents started. It just happens to be like a moment in time when all the continents happen to bump into each other.
Right.
Right. And so they were separate before, and there were different continents before. There were different oceans before. But at one point in time, all the continents bump into each other and we have Pangea. That's hard on life. Continental climates are extreme. Think about the middle of Siberia. It could be 100 degrees in the summer and it could be, you know, minus 50 degrees in the winter, right? Yeah. So continental climates are extreme. And then when the continents are all together, all the organisms have to compete with all the other organisms. You know, some of the problems we have with invasive species today. Mm-hmm. Well, that's because an organism from over there is now competing with the organisms over here. But when the continents push all the organisms together, it's just hard on life. So we're in a rough time to begin with. Mm. And then these giant volcanic fissures in what is now Siberia open up and issue forth vast quantities of greenhouse gases. And we get into this like runaway greenhouse effect, and the planet just heats up
everything
tremendously. And the combination of all those things is just too hard on life. and 95% of species perish.
Whoa.
Yeah.
And so we were pointing out that a lot of the species that perish include dinosaurs. And this was during the era where the dinosaurs were like cat-like size, you said?
Not yet. You've moved
Not
ahead
yet.
one.
I'm
Yeah.
ahead
We
one.
don't have dinosaurs yet.
That's why
during
you're
the Great
here, Ken.
Dying.
You got to keep me on order.
Yeah. So this is a world before dinosaurs. This is the end of the Paleozoic.
Okay.
So pre-dinosaur world. And this sets the stage for the dinosaurs.
Okay.
Have you ever seen those little cute fossils called trilobites? They're very common. You buy them in rock shops, and you can go on. You can find trilobites.
Maybe I've seen one. I just can't remember
Look on
the term.
Etsy, and you'll see
Okay.
like jewelry made of trilobites. But they go extinct at the end of the Paleozoic, and lots of other things too. There you go, trilobites. So they had a great
I've seen that.
great run across the Paleozoic, and then they can't hack it when this happens, and lots of other things go extinct as well.
Got it. But it set the stage for the dinosaurs.
It set the stage eventually for the dinosaurs. Kind of set the stage more for the crocodiles, and then the next one set the stage for the dinosaurs.
Okay, and the crocodiles, these are the ones that are bipedal you were talking about?
Some
that are
were.
running around?
There were other ones that were quadrupeds, but they were huge and scary, and yeah.
Now, how, like, because I've talked with some other people about this, about how we as humans look at time. And I was talking with Gnostic Informant about this. I don't know the exact term, but it's almost like there's an exponential correction that we do in our heads. And what I mean by that is we look at something that's attainable to look at, meaning like we have video of it, for example, of like the 1940s. And it seems very long ago.
Mm-hmm.
But then as we go farther, maybe we go 200 years back before that, we view that on a similar layer as we viewed the past 80 years. And then from 200 years, we look at the 600 years before that, and we view that like almost in the same time period, to the point that, we could be talking about something that happened in 65 AD and compare it to something that happened in 168 AD. And in our heads, we're like, oh, it's similar time. Yet
Right.
it's
Yeah.
like 5 generations apart,
Yeah.
and shit changed and everything.
Absolutely.
So when we're looking at evolution, I get caught in that trap all the time, because you almost like picture like, oh, just walked out of the water and boom, there it is. But how long after that extinction, like what was the process of the first crocodile forming, and how long did it take to grow to size?
On a human time scale, it's an immense amount of time. I mean, you think about events that happened here on Earth 1,000 years ago, and it seems so long ago.
But it's
right?
nothing.
But it's nothing geologically, right? 1,000 years is like 500 oak trees.
Right.
Right. So, it's to us, to our perception, these things move at a rate that's not perceivable. Right. Geologically, when you look at the whole fossil record, you can see things that look like they're happening very rapidly. But, our senses are tuned for the here and now, right? Like we're very good at perceiving threats, food, and mates, right?
Yes.
We're not so good at perceiving things that unfold over years, definitely not decades. It's one of the reasons why people aren't, I think, as alarmed as we should be about the climate crisis and the biodiversity crisis. I mean, we go outside and today seems a lot like yesterday, and this summer seems a lot like last summer, but it's not. We're just not built to perceive the kinds of changes that are happening in this world. And what really scares me, like less than a year ago, the World Wildlife Fund issued a report, and now I'm talking in numbers of animals, not species. Since 1970,
Yes.
in terms of larger creatures, not insects or microbes, since 1970, 72% of wildlife has disappeared on the planet.
Crazy.
72%. How is
Crazy.
that not on the front page of every newspaper every day?
Because people are still getting their Chick-fil-A and, doing their thing
Right.
and going about their 9 to 5.
We're not perceiving it. But, I notice it when I was starting my career, right? And I was a young paleontologist, and I'd go out to places like Wyoming in the summer, and I'd get a pickup truck, and I'd drive across the state. I'd have to stop and squeegee the grasshoppers off my windshield about every 20 minutes because you couldn't see otherwise. I was out in Wyoming a couple summers ago and drove across the state. I don't think a bug hit my windshield.
Whoa.
That's bad. That's
Yeah.
bad. If the insects aren't thriving, nothing else is going to thrive. And but these changes happen so slowly on a human time scale that we don't see them.
Yeah, and I think also the really unfortunate stuff that happens with this is we're so flawed as humans in the process as well, and so you'll get people to take advantage of these things and who don't really even give a shit about anything that's happening, and they'll try to say, well, more for me, less for you, and that's something like when you're trying to have a good conversation about, well, is going on with our climate? What have we done since the Industrial Revolution that's affected our atmosphere and different aspects of like how this place works? You know, it ultimately comes back to, well, the buck's going to stop with either totally free corporations doing whatever they want or the government shutting everything down and telling every people what to do. And both extremes piss off a huge semblance of the population, no matter where you go. And we kind of live in this world where it flips back and forth like that. And so I worry that like we can't have these conversations because people either like completely say all true or all false, and you don't get anywhere with it because it's also like a lot of people out there who aren't scientists as well, and they're trying to make a decision on what that is. And I don't think that should be room for scientists to say, well, we're the only people that are allowed to talk about this, to be clear. But I also think like we have to get back to the like, well, what is the empirical evidence here? What has changed? What's something that's a part of, just a phase of change that happens over time versus things that look permanent that we're doing that could be causing an extinction. And then somehow you got to start that conversation with people and, think about 1,000 years from now, which is, as you've just laid out beautifully, it's very hard to get people to think about 1,000 seconds from now.
Yeah.
Now they're going to think about 1,000 years. It's tough, man.
Yeah. Well, I mean, science is in economics. It's not economics, right? So we don't necessarily have the answers there. It's not politics. We don't necessarily have the answers there. But we have the data, and we know how the world works better than anyone. I mean, think about it. How does every single disaster movie start? With a scientist being ignored.
That's right.
Right? It's true.
It's very true. Or I Am Legend with a scientist telling everyone that we cured cancer.
So what we try to do at the Edelman Fossil Park and Museum is give people a deep time perspective and a deep space perspective. Because when you start to look at it that way, if you pull back and, in the Apollo 8 mission, the first one to go to the backside of the moon, astronaut Bill Anders took that famous Earthrise picture where you see the Earth rising up over the moon.
Yes.
Iconic picture. It's credited with really kicking off the environmental movement. But when you see the planet that way, there's no us and them, right? And there's no anywhere else either. Right. We live on this tiny little rocky lifeboat in space. And I try to get people to think. I gave a talk last night, and I asked the audience, like, imagine, there it is. Imagine you're adrift in a little lifeboat in the Pacific Ocean with like 4 or 5 other people. Like, how much are you going to care for that lifeboat? How much are you going to think about it? How much are you going to dote upon it? How quickly will you be to repair it? How much are you going to love that lifeboat? Well, you pull back into space and get that picture. That's our situation.
Right.
We live on this tiny little lonely lifeboat in space. And I'm sorry, Elon Musk, there's no planet B. We're not going to put 1 million people on Mars. You know why?
It'd be very cool, though.
Because Mars is terrible. No, we're going to go to Mars. We're going to plant the Explorers flag on Mars, the Explorers Club flag. But Mars doesn't have niceties like drinkable water and a breathable atmosphere and a magnetosphere to protect us from the sun's deadly radiation. We have an entire continent on Earth, Antarctica, that we don't even have a breeding population of humans on. I looked it up. There's been 11 babies born in Antarctica. 11. Yeah.
Were they born in the Nazi bunker that allegedly exists there?
I don't know about that.
Ooh, uh-oh.
But I have heard of
I've
heard of the McMurdo marriage, the Tarmac divorce. I think that probably relates to that.
I don't know what that is.
I think, there's a long winter in Antarctica, and so I think people, get busy.
It's an interesting point, though, because there are places that we can't even inhabit here, and we're trying to figure out how to do another planet. I love the idea. Like, it's great to shoot for the moon.
Yes. But this is our home, and, we have this planet that we are exquisitely adapted to and for, and it suits all of our needs. It has everything we need, and why? Preserve this little lonely lifeboat that we have, because it's really all we're ever going to have him, and we're not going to send, a rocket ship to another star system and colonize that because we can. If you wanted to go, well, here, if you go to, like, if you want to send an intergenerational mission to, say, a planet going around Alpha Centauri or Beta Centauri, it's a little closer. Well, those people are going to leave Earth and never return, right? And so it's a multi-generational mission. How does speciation happen? It always happens in the presence of geographic separation, right? Go back to that biological definition of a species. It's a group of interbreeding organisms. When they get on that spaceship and they leave and they take their genes with them, never to mix with our genes again, at that moment, they're a different species.
That's so interesting. So I never thought of it that way.
So yeah, we could send another species to another star system, but it's not us anymore.
So I don't know, maybe this will come back parallel. Maybe you can shoot me down and it's not, but like, you've seen the movie Interstellar?
Yeah.
Before? So technically Matthew McConaughey leaves the Earth, only a certain, I forget what the exact time was, but only a certain amount of time in his life passes, not a ton of time. But when he gets back to Earth, it's now been 80 years, right? So he was in a time warp. And so I've always looked at it with if I'm just looking at it definitionally, the argument there is that he's actually an alien because he's returning to a place that he's never been to before, in a way, you know what I mean? Because his time didn't pass, but theirs did. And I think what you're getting at with the interspeciation and what a gene pool would do if it left here is a similar idea. It's like, yes, let's say there's men and women on that flight, right? And they go there and maybe they breed together in their new place. They are going to at some point be starting a new species there because it's a different environment, different adaptation happens. Maybe there's interbreeding with whatever's there. And now you get a whole new type of world.
Even just random genetic drift. I mean, their genome is just going to go to a place that ours are not, right? And so, eventually, given enough time, we wouldn't be able to breed with them, which makes us a different species.
And time could be 300 years or 300 million years. It's hard to say. But
it'd be more than 300. It'd be a long time.
It'd be a very long time.
But it would happen.
Because we started this conversation talking about how long it might have taken crocodiles to form into a crocodile after that third extinction. And it's like, again, this is where you get into hundreds of millions of years. It starts as a little bug or whatever in the post-apocalyptic world and then eventually works his way up to this, what'd you say, 15-foot bipedal thing running through the woods? I mean...
Yeah. I mean, in the case of us vertebrates, we go back to a very particular lineage of essentially little wormy-like creatures that eventually develop, it's called a notochord. It's like a stiffened central nervous system, and then that eventually becomes ossified to form a spinal column, right? And then that's when we have vertebrates. And then so we wouldn't go from like a bug to a crocodile, but we go from these precursors of vertebrates through vertebrates to, all the creatures with bones that we have today.
Over a very long period of time.
Yeah, that's hundreds of millions of years.
Hundreds of millions of years.
Yeah.
So dinosaurs, going back to that, you said they were like apt to form during this period. This is when they form into like the cat-sized creatures. And how long was that period before the fourth extinction or fifth extinction, whichever one?
So dinosaurs formed near the end of the Triassic period. That's about 237 million years ago. And then really the dinosaurs kind of become what we think of as dinosaurs in the Jurassic period. That's when they become very biodiverse. That's when they start to conquer new lands. That's when they get really big. That's when we see the first giant dinosaurs.
What percentage of the planet of species do you think dinosaurs were at the time, based on all the other species that were there? Is it 40%? Is it 10%? Do we know?
Well, big creatures are never a large percentage of the species. Most species are bacteria, right?
That was a dumb way of asking that. Excluding things like insects or very small things, as far as like in what we would now term like mammals or stuff like that. Like what percentage of larger animals?
Yeah, in terms of, let's call it macrofauna. Let's say that. A very high percentage. I mean, dinosaurs on land, right? Dinosaurs dominated the terrestrial ecosystems for the better part of 165 million years. Our ancestors, our little shrew-like mammals, We evolved first about 20 million years after the first dinosaur. So out of that 165 million year run, we're there for almost all of it, our mammalian ancestors.
Not humans, but the
No,
mammalian ancestors.
your great-grandma was a little shrew-like creature back in the Mesozoic. They have a tough time competing with dinosaurs. So mammals, for the most part, they go nocturnal. They all stay small. They're living really in the hidden and forgotten recesses of the dinosaur world, hoping never to be noticed. That goes on for an unimaginable amount of time. And then the dinosaurs are wiped out in a cosmic accident, and the surviving little tiny mammals can now walk out under the blue sky, and they don't have the threat of dinosaurs anymore. And they quickly evolve into the mammalian fauna that we see today. It's not long before we see the first proto-primates. It's not long before we see proto-whales and the earliest artiodactyls, things with hooves. And, all of a sudden, think of an ecological niche as like a job description. And all of a sudden, like, the Great Depression comes, like all the jobs are just wiped off.
Yeah.
And now all of a sudden we're in an economic boom, and now there's all these unopened, these unfilled job positions, and mammals quickly evolve into all of those. And we have this burst of radiation. It's called evolution. It's called an adaptive radiation. And all of a sudden, it's the age of mammals.
Now, to go back for 1 second, though, because there were 3 official eras of dinosaurs before the asteroid hits. The second one is the Jurassic one, and you said that's the one where they start to get really big and the dinosaurs we recognize.
Yeah.
How did the Jurassic end, and what did dinosaurs look like on the other side of that for the third period? Did they kind of have to start over in size?
No, there's extinctions that happen at the end of the Jurassic that we use to define it, but they're more minor extinctions. It's not one of the big 5 mass extinctions, so it's not a huge cataclysm. These are more subtle changes that are happening, but enables paleontologists to know you're in the one period versus the next.
Okay, so
but it's not so earth-shattering like the big 5.
But the species basically survived then in that case. So you might have a T-Rex in the Jurassic period, and you still have a T-Rex.
Well, T-Rex are only at the end of the Cretaceous period.
So I couldn't even get that right, damn it.
Species, generally, I mean, as a rule of thumb, high amount of variability in this, but as a rule of thumb, species persist about 1 million years before they turn into something else or maybe go extinct.
Where did the T-Rex come from? Let's unwind that one.
Asia.
Yeah, but where, like, what did it start as, or maybe not start as, but like what would we know it to have evolved from?
Well, first we have theropod dinosaurs, and these are among the earliest forms of dinosaurs. But then later, much later, there's a group of dinosaurs that we would call the tyrannosauroids, which are, and there's over 24 of those known now. And it seems like the precursor of the North American tyrannosaurs came over from Asia. Asia was connected about where Alaska is to North America. And then T-Rex shows up right at the very end, evolves right at the end. So, dinosaurs lived at different times, but T-Rex happens to be alive when the meteor hit. It's found in Montana and Wyoming, but also Texas. And so there were probably T-Rex that saw the asteroid coming in and died that day. Triceratops was alive at the moment that the asteroid came in. Other things like, Allosaurus, Stegosaurus, Brontosaurus, they're Jurassic. They were not around for this event.
Oh, they were already gone. So they were killed in the previous extinction.
They're Jurassic. They not necessarily killed in extinction, but, species last for some time, and then they either turn into something else or they go extinct.
Was the T-Rex like the king of the jungle at that time, would you say?
T-Rex is, obviously the most famous dinosaur. It's not even close. And honestly, it's worthy of its extra measure of fame. T-Rex was huge. It was powerful. It was fast. It could smell really well. It could see you if you were moving or not moving. That's a Jurassic Park myth, right? So T-Rex is about the most badass thing that's ever walked on land.
What are some, Jurassic Park is obviously like a supernatural movie and all that. So I'm sure as a paleontologist, some of it makes you bang your head against the wall. But what are some themes there that they really did get right?
Well, so first, I love the Jurassic movies. I mean,
you do?
they're fun summer monster movies.
Good for you. I like that.
And like, if they inspire you, then go to the library and get a book about dinosaurs and learn something, right? But there's a whole generation of paleontologists a little younger than me that have their origin story with when Jurassic Park came out in 1993. And
that's cool.
So, and I'm sure every time one of those Jurassic movies comes out, there's a new batch of paleontologists that are born as a result. And, you know, and geneticists as well, and probably all kinds of other scientists. So they're great and they're fun and you know, I love them. They get a lot of the science wrong, but you know.
Is there stuff they get right?
Yeah, I think so. But there's some stuff that, like, you know how big a velociraptor skull is?
No.
It's about like that.
And they made it way bigger.
Way bigger.
Right.
So a velociraptor
They got to sell a movie though.
is little. A velociraptor is more like a pissed off turkey.
Oh.
Right. Yeah. Like
turkeys will get you.
Well,
they run at you hard.
You could take a turkey, I'm sure.
You could take it.
You could take a velociraptor. If there's a velociraptor in your kitchen, it's more of an opportunity than a problem. You just like open up a can of cranberry sauce and preheat the oven and, you know, yeah.
It's going to climb in.
Well, you'd have to do something. But, you know, it's probably good eating. Probably tastes like chicken.
You telling me chickens are little velociraptors?
Well, chickens are dinosaurs.
Yeah,
so we
they are.
literally know what dinosaur tastes like.
They are. I eat chicken every day, so I'm eating a dinosaur.
You're eating dinosaur. Yeah.
Wow.
Dinosaur flesh courses through your blood.
Chickens are not the brightest though. Like
they are not.
Yeah.
I have chickens. They're really dumb.
Oh, you have some yourself.
Chickens.
Do you like cook them or?
No, they're pets. They
they're
have
pets.
names.
Oh, sorry.
They have names. We bury them when they die.
Oh.
Yeah. So,
sorry.
But they're dumb. They're really dumb. So we have, imagine we've got our deck is here, and then the chicken coop, and then the door to the chicken coop is on the far side. So I'll go out on the deck and I'll throw pizza crust in the backyard, and they can't figure out how to get to it, even if their door's open. They'll like bang their heads on the fence, and then they start to walk to their gate and they look around and they're like, but the pizza crust is getting smaller. Yeah. And then they run back to it, and it takes them it's like a Rubik's Cube. It takes them like 10 minutes to figure out that they have to go away from the pizza crust before they can get to the pizza crust. They are not smart animals.
Are they nice to you? Like, do you get to pet them or?
We've had chickens for a long time. I've only had one that like made friends with me because
if they were bigger, they'd probably eat you.
It remembered that I gave it some goldfish crackers on the deck, and then it would come up like every day looking for some goldfish crackers, and it would sleep next to me while I'm reading a book or something.
Yeah, they're nasty. I mean, you ever seen a cockfight?
No, I never have.
Listen, I've seen it in movies. That's enough for me.
That's actually the first time anyone's asked me that, but I've never seen it.
They can. It wasn't a pause, but still, like they can go at it. And I always think like they're like this big.
Oh yeah.
And we cook them all the time.
They're really mean to each other, especially if one of them gets injured and they see the red of the blood, like they will just attack that poor chicken. Yeah, you can see.
It's like the fucking Hunger Games out there.
You can see. I made a slow motion film of our chickens running across our front yard, and I put the Jurassic Park music in. It's on my Instagram feed, and they're dinosaurs. I mean, you can see it when you see these chickens in slow mo going across our front yard.
Yeah,
dinosaurs.
They look like
it's
a
pack
raptor
of dinosaurs
in a way. That's crazy.
Yeah.
So, were there any dinosaurs? Let's look at the Jurassic period. Were there any dinosaurs that we can use science to determine, I don't know, by brain size or things that we find that you would characterize as very intelligent?
Well, yeah. I mean, we have some alive today. Crows are super smart. Parrots are super smart.
Pigeons?
Pigeons are pretty smart.
Yeah.
They certainly have an unbelievable sense of direction.
I have an ongoing feud with my buddy Mark Gagnon. He thinks pigeons are like not smart at all, but I'm like, they're a top 10 smart animal.
No,
pigeons will literally crip walk out here. It's crazy. They're like going side to side. Very cool.
Yeah, no, they're remarkable animals, really.
Yeah, so they're a dinosaur.
Yep, pigeons are dinosaurs. A ruby-throated hummingbird is a dinosaur. A flamingo is a dinosaur. Mosasaur is not a dinosaur. Plesiosaur is not a dinosaur. Pterodactyl is not a dinosaur.
When did the pterodactyl go extinct at the asteroid too?
Pterosaurs did, yeah, the larger group. Yeah.
So they're not dinosaurs. Mm-hmm. What did we characterize them as again?
Well, they don't have like a very marketable name. They're in a group called the Pterosauroidea, and then they have Ornithodyra is the bigger group that they're in. So dinosaurs and pterosaurs are united in a group called Ornithodyra.
Ornithodyra.
Yes,
And there's
it's not the
nothing
best
that
name.
still exists of that.
Birds. Birds aren't pterosaurs, but the group Ornithodyra includes all dinosaurs and the pterosaurs.
Wait, hold on. Back that up. I got to make sure I went in my brain right. Say that again, if you don't mind.
So you can unite any two creatures in a larger group,
Yeah.
right? Like us and a earthworm are in the really big group called Animalia, right?
Right.
We're both animals. So any two creatures are in some group together. So the group that pterosaurs and dinosaurs are both in is called Ornithodyra.
Okay. So it's a part of a larger tent.
Yeah,
so
that's
we
the
can
larger
trace
tent.
birds to them, but birds are traced to both. But at the top of that tent where you have the Ornithodyra and the dinosaurs, the Ornithodyra were totally separate from the dinosaurs and cannot be traced.
Well, think of here's the dinosaurs, here's the pterosaurs.
Yep.
Right. This is Ornithodyra. And then dinosaurs
Got it.
branch, and there's lots of branches here, right?
Got it.
So Dinosaurville here, pterosaur land here,
Understood.
right?
Okay. Now, what other, large species, maybe we can actually talk about what you already hinted at earlier with what was going on in the seas back then, but during the Jurassic period, what other large species besides dinosaurs were existing and thriving?
Well, on land, there's not anything
much.
else that's really big besides dinosaurs.
Mm.
And then in the ocean, at various times, large marine reptiles have evolved. But again, they're not dinosaurs. But plesiosaurs, and which are like whale-sized creatures. They look like the non-existent Loch Ness monster.
The plesiosaurs. Can we pull
Yeah.
this up?
Yeah,
Let's see this.
yeah,
Whoa.
yeah.
Yeah, let's pull that first one, Joe. Top left. So that's a plesiosaur.
Yeah.
Plesiosaur right there.
Yeah. So there. Yeah.
Whoa.
Yeah. So those are really scary sea monsters, and they were real. And then the mosasaur.
Where did we find their fossils? Did we find any of that like on land because it used to be where sea is, or?
That's right. We find them in marine deposits that are on land now.
Got it.
And so originally they were found in Northern Europe, like in the Netherlands, and in southern England.
Mm.
Yeah, in the Dorset coast is a great place for that. Pull up the mosasaur, the Mosasaurus. That is the all-time apex predator ever of the oceans.
How big are we talking?
They could get to be like 55 feet long.
Oh, fuck that.
So there you go. That
God.
second picture is a good one there.
It's like a killer whale meets a great white meets a T-Rex of the sea.
Yeah, I mean, so they're 55 feet long. You know what a Komodo dragon is?
Yes.
It's a marine Komodo dragon, essentially. Yeah.
You ever seen those things eat a goat?
Oh, yeah, they're
Bro.
They're monsters.
Yeah.
So imagine a
Joe's
marine
Joe's
Komodo
getting
dragon.
some post-traumatic stress back here.
As long as a school bus, paddles for limbs, 6-foot jaw, and then they have a second set of teeth at the top of their throat that points backwards to keep you from swimming back out. You
I
might be able
hope
to
you're
see
just
it.
dead before you get there. You know what I mean?
Yeah.
Like they already
Yeah.
get you. You're dead. I'm not trying to swim back out.
Yeah.
Whoa. Is that it? Is eating supposedly like a great white shark?
Well, they didn't
Like
exist
for
then,
si-
but
yeah, but for
there were
size
lots
comparison?
of big sharks. I don't know if you can see those back of the throat teeth. They're called the pterygoid jaws. So, look, the upper left-hand picture shows those extra set of teeth in the mouth.
That's a dragon of the water.
Yeah, right there. If you zoom into the mouth, you'll see those extra teeth.
All right, let's see how close we can get there, Joe. Oh, yeah, I can kind of see it already, but I don't know if people out there can see it. It's in the back. You're saying
Yeah.
it's like, yeah.
Yeah.
Whoa.
So maybe my favorite fossil that we found at the fossil park is we found one of those pterygoid jaws with all the teeth in it. And what's amazing about our location, so again, the fossil park site was underwater in the Cretaceous period. In our second gallery called Monstrous Seas, everything in that gallery was found on the property in a layer that goes about 65 feet under your feet where you'll be standing there. And these creatures lived here. So when you see our giant Mosasaurus, if you can pull that up, if you search for
Like the word
Allaman
Moses.
Fossil Park and
Moses and
Mosasaur.
then Aris on the end. Is that
You'll
why they
see-
named it that?
No.
Because no. Okay.
You'll see a 55-foot-long mosasaur, and like in the fullness of time, it's nearly a statistical certainty that a mosasaur of that size was in that position, right? Where you see it in the museum today. Yeah, there's our mosasaurs.
Oh, that's yours right
Yeah,
there.
Yeah, that's the museum.
Whoa.
Now,
and that's
our-
actual size.
Actual size, and there was almost certainly one right there. 66 million years ago. So we have an amazing paleo artist that did over 50 full-scale reconstructions for us like this. It took him in his studio outside Kansas City more than 3 years.
He's a paleo artist? That's
Paleo
a thing?
artist. His name is Gary Staab, S-T-A-A-B. He's the world's greatest paleo artist. He used to win the National Geographic Paleo Art Award every year until finally they made him a judge so somebody else could win.
Whoa.
So he does an unbelievable amount of research.
How does he go? I mean, this is such a broad question, but how does he go about doing that? Like he gets maybe not even a full set of bones, but he gets enough to have an idea of a structure. And then, I mean, how accurate is it, I guess is the question.
It's as accurate as it can be.
As it can be.
So Gary first starts with a tremendous amount of research. And, you know, he would never call himself a scientist, but he's a damn good scientist. And he has an unbelievable breadth of anatomical knowledge. And so he starts with that, and then he will make a 1/10 scale clay maquette of that. And we iterate on that to get the pose right and everything. And then he scans that, and he uses a CNC machine to cut about 8-inch foam slices. And you can imagine how many there would be in a creature
lot.
like this. Glues them all together, and then puts resin or something on the outside, and then starts to sculpt all the scales. And he'll say, you know, you start at the tail, and then a couple 100,000 scales later, you're done. He makes the eyes himself, he makes the teeth himself, and then he paints the whole thing. He puts in pathologies and scars and things like that.
That's amazing.
And they're unbelievably lifelike.
That's amazing. I got to come visit this.
You have to.
This
Yeah,
is so
you have to.
cool. I can't believe this was right there
Right there.
the whole time.
It's behind the Chick-fil-A.
I know. God damn it. He's like, yeah, there's a massage parlor in the back.
That's not true.
Wow. So this would have been swimming
Yes.
right approximately where it is.
And you would have been dying.
Yeah.
Yeah.
Now, take me back to that first day when you guys found something there. Because you've been doing this all your life. I do want to come back to like how you even got into this as a kid. We'll get there. But like, what was found, and did you have like the Dr. House moment where you just like look up and you're like, holy shit?
I didn't. I've had that moment elsewhere in the world.
Oh, you have? All right, we'll get
I
there.
have. But here, you know, it was like a muddy pit that was being mined for marl sand. You know, when they were mining it, it was always kind of a jumble. And I didn't think much of it. This is back in 2003. And I thought, well, you know, I could bring my students here. They could find some fossils. That'll be cute. And then I'll go everywhere else in the world to do my research, you know. So it wasn't until, you know, as I said before, when the quarry owner told me that they were going to go out of business, that I managed to secure a corner of the quarry. And when we started to excavate methodically, then I started to see what we had there and its scientific importance. And then I knew I had to find a way to save the site.
Right. But so when you started to figure out, maybe the question isn't the first moment there, but when you started to figure out, like, oh my God, we just found a dinosaur bone there. You gotta be thinking, oh my God, I grew up in Linwood, New Jersey. This is like 50 miles from where I grew up, and this is where it happened, right?
Well, it didn't surprise me to find a dinosaur bone there, because people don't know this, but southern New Jersey is like the cradle of dinosaur paleontology.
And you knew that before all this.
I knew that, yeah. So dinosaurs were first recognized from really scrappy remains in England. And so in the early part of the 19th century, bones start turning up about an hour south of London in the Tilgate Forest and other places. They can't really tell what they are because the remains are so scrappy. And that's how they get the name dinosaur. In 1841, a British anatomist, Richard Owens, gives them that name. He buries it on like page 240 of the Mesozoic reptiles of Great Britain, because he doesn't even think it's important. And he says there's a new tribe of crocodile lizards, is what he calls them, and he gives them the name dinosaur, which means terrible lizard. So he thinks they're just these big puffed up lizards.
Thank you guys for checking out this clip. If you haven't already subscribed, please subscribe and hit the like button on this video. It is a huge, huge help. And if you'd like to check out this clip's full podcast episode, that link is in the description below or right here. And finally, you can follow me on Instagram and X by using the links in my description below.